Tonight, we will explore the science behind how colors are displayed on modern screens. Understand the technical principles involved, then build a practical, interactive color picker as a project, in design that you can replicate in any programming language. Fully customizable and resizable. Probably not a great idea to make it resizable in real time. Most digital screens display colors using a system called RGB, which stands for red, green and blue. Each pixel on your screen is made up of 3 tiny parts called subpixels. 1 red, 1 green and 1 blue. These 3 subpixels can light up at different brightness levels. By adjusting how bright each one is, the screen can create a million of different colors through a process called additive color mixing. When all 3 subpixels are fully lit, the pixel appears white. When they are off, it looks black. The screen rapidly controls these subpixels across all pixels to produce the images and colors you see. It's the year 1850. In a quiet German town Stettin, a visionary mathematician named Hermann Grassmann is deep in thought, fascinated by the mysteries of light and color. He's exploring the nature of how colors blend. At the time, scientists knew that shining red, green and blue light together could produce white, but they didn't fully understand why. Grassmann, driven by curiosity, begins to develop mathematical ideas about how different colors of light combine. His groundbreaking insight, later called Grassmann's law, explained how these colors add up, laying the foundation for modern color science. Little did he know, his work would eventually help shape the screens and displays we use every day. Grassmann's curiosity changed how we see and create color. And now we are going to build it. You will be in control of 3 subpixels, red, green and blue, that work together to generate any color you want. First, let's specify the desired functionality. The user will have 3 independent sliders. Each slider will allow us to set the brightness of each subpixel in the range of 1 byte, that's 0 to 255. Each slider will mark the current value visually and allow us to change the brightness of the subpixel to the left or to the right, making it darker or brighter. Big question: how to represent this machine? Most importantly, we will need to store the color itself. Our pixel structure will hold a color in 3 bytes, red, green and blue, each from 0 to 255. The second data structure will represent the color picker itself. It will hold our pixel structure and number of possible colors on the slider. We will specify the sizes of the single color rectangles and also padding between them. Additionally, we need to specify the start position on the screen and how far the color picker will reach. Lastly, we will define the delta color between the rectangles, or 1 step of the gradient. Let's take a look at the interface before we jump into the implementation. First, in the main thread and only once, we will call the constructor of the color picker. This way we will receive its instance that will be used until the application is terminated. After we break the infinite application loop. Before that, during the calculation of each frame of our program, we will call the render method on our instance. This will make our color picker visible to the user. Ta-da! Nonetheless, the picker doesn't do anything yet. Before we do anything else, we need to obtain the data from the mouse. We need boolean value, is the button 1 clicked? And we need position of the mouse on x-axis and y-axis. Now our logic is divided into two parts. Either the mouse is positioned on the image and we are going to draw a line using the color from the color picker, or the mouse is positioned on the color picker and we are going to pick a new color and update it. And that's all there is to it. Let's go ahead and take a look at the implementation of the color picker. And start with the most boring one, a constructor. It just takes the configuration from the parameters supplied and creates the instance and returns it as a reference. In the meantime, it also precalculates the end position of the color picker. Alright, now something more interesting, the render method. This method makes all the colorful elements of color picker visible. Firstly, it will draw a gray rectangle that will encapsulate all the elements of the color picker. Then we will render all the colorful elements inside of the for loop. We will iterate from 0 to number of colors by the color increment. This way we will render the RGB subpixel rectangles horizontally. For each subpixel we calculate the rectangle color. If we are standing on the selected rectangle, we mark it, either white or black. If the sum of values from RGB subpixels is higher than 3 times 128, we mark it black. And if it's lower or equal, we mark it white. And we repeat this for each color, red, green and blue. Our next step is to take a look at the update colors method. This method is invoked when the user clicks on the color picker. It takes the mouse position and compares it to each subpixel section. And if there is a match, we update only the affected subpixel. Now we have two last methods to go over. getPixelColor is just encapsulation of the current pixel color. No additional value added. And the method calculateFullDimensions is calculating the end positions of the color picker, repeating the logic from the render method without actually rendering anything. The only purpose of this method is to calculate the dimensions of the color picker before it is rendered. So the other elements of the graphical user interface can be moved accordingly before the rendering process starts. This method is invoked when the user clicks on the color picker. When all three subpixels